Hello, everybody. My name is Nodirbek Avazbekov, and I'm a student in Universitas Negeri Malang in the Faculty of Engineering program of Civil Engineering. And this is my project from physics. My NIM number is 2505 2362 2300. Today, we are going to talk about work and energy. So, for this topic, our source will be the physics book for scientists and engineers with modern physics, 9th edition, which was written by Raymond Survey and John Jewett. So, first, we need to talk about what is work in general. Work is the energy transferred when a force causes an object to move. In this case, we have this stickman, which moves a box from one place to another. The distance that the box crossed is the difference in displacement, while the force that is being exerted is the force that the stickman applies to the box. We have a definition for work done by constant force, and for work done, we have different formulas for each work done. So just let's stick together. The first one is by constant force. The work done on a system by an agent exerting a constant force on the system is the product of the magnitude of the force, the magnitude of the displacement of the point of application of the force, and cosine theta, where cosine theta is the angle between the force and displacement vectors. So just to be simple, it's just work done equals force applied multiplied by the distance that it crossed, the object crossed, or the change in displacement multiplied by the cosine theta, where theta is the angle between the force applied and the displacement. And that's it. That's simple. You can see the definition that we gave in this picture. You can see that there's a theta, the angle between force applied and displacement. You can see that the object has moved, which causes change in displacement, and then the force being applied. So just simple. Next, we can see that there's another example. In this figure, it also shows us the normal force and then the weight or the just weight of the mass. So in this case, we only have the displacement horizontally. So for this kind of equations, they may trick you by asking what is the normal force, what is the weight, like what is the work done by weight and normal force, which is just going to be 0 because there is no vertical displacement, just as simple as that. Now, you can notice that the scalar multiplication of two objects is equal to two objects being multiplied by cosine theta. Cosine theta being the angle between these two vectors. This actually looks similar, the same as the work done. And it is true because the formula of work done comes from this formula. And then in this case, force vector is multiplied by the displacement vector. We can see it in this figure. You can replace the B vector with the force vector and A vector with the displacement vector for us to have the force vector on the same line and horizontal line with the displacement vector. We actually need to multiply it to cosine theta. Now, sometimes our force is not constant and it varies. And if it's related to x, we can make a diagram out of it. Actually, we can make a diagram like even if it doesn't. So in this case, we can see the y-axis is the force and x-axis is the displacement. In this case, to find the work, we just need to find the area below of the line that it produced. And we can use the integration or just normal geometric area finding equations for us to find the work done. So if you want to write this formula in integration, we can just write it as such. W work done equals to integration of force multiplied by the displacement, difference in displacement or the slice of displacement, while the border for integration being x final and x initial, x final being displacement, final displacement, and x initial being initial displacement. We're going to use that formula to find other works too. For example, the first case is work done by a spring. In this case, if the spring is compressed, we have a force, which is force equals to IK, which is the constant of spring, and then multiplied by x, which is the displacement or the distance it moved. From the high school, we already know with the formula, work done is equal to minus kx squared divided by 2. But for us to understand where it came from, we're going to look at it now. So this formula comes from the integration formula, which we just learned now. And then you just put the force, which is minus kx, to the formula that we just learned, which will give us this initial formula. However, in the initial formula, after the integration, you can see that we have two values, not one, two. That's because the previous formula suggests that the initial displacement is 0. But in this case, we have the initial displacement too. So which formula you want to use, it depends on the task, what task asks you. If the task says that initial displacement is not 0, has a value, then you're going to use this. If the initial value is just 0, then you can use this formula, but the 1.5 kx squared initial will be still equal to 0. Now, let's see the kinetic energy. The kinetic energy has the formula of kinetic energy equals to mv squared divided by 2. While the actual formula for the force is actually m multiplied by a, or it's just m multiplied by velocity over time, or m multiplied by acceleration. You may ask why. That's because it still uses the same formula in which the force varies. In this case, you can see that our m mass multiplied by acceleration can be written as mass multiplied by difference in velocity divided by difference in time. And then if you put it to the formula, you will have this, the one that you are seeing now. And then we can just put dx over dx, which is just equal to 1. But for us to create a new formula, which is actually related to velocity, in this case, we can write it as such: dv over dx, and then dx over dt. Dx, difference in displacement over this difference in time being our just velocity, while the difference of velocity over difference of displacement multiplied by difference of displacement just leaves us with difference in velocity. That's why our initial formula that was ma becomes the same as mass multiplied by volume, mass multiplied by velocity multiplied by difference in velocity. And if we integrate it, we're gonna have the formula that is below, which is 1.5 mv squared final minus 1.5 mv squared initial. Even in this case, we have two values, not one. That's because there might be a possibility that our object was already moving, and then after some time it gained more, because of the acceleration, it gained more velocity. That's why if the question asks you, like if the question gives you that the initial velocity has a value, then you use this formula. If it doesn't, or if it just says it was 0, then you're just going to use the formula which was before, or just this formula, but the initial velocity, the work done by initial velocity will be just 0. Now we have potential energy. In this example, we can see the guy, like a boy, falling down, and h is the displacement, but it's vertical displacement, difference in vertical displacement. For this, the force done, the work done is uses force, which is equal to mg, g being acceleration by gravity, which is 9.81. In potential energy, from high school, we know that it's equal to mgh. But let's see, like, if you put it in vector multiplication, or if you use like vectors for multiplication too. You have the example here in which we are lifting the book, and the force is equal to mg. So the book is being lifted with a constant velocity. And then we have change in displacement, which is yf minus yi. So in this case, you can just multiply the weight to yf and minus yi, which will be our displacement. This uses the constant force equation or formula. Yeah. So now let's review some questions and examples. These kind of questions may appear on your exam, but however, there might be a possibility that they'll be a bit more difficult. That's why if you want to review the topic more, and if you want to solve some equations, you can do it online from another videos too. In these equations, we have a graph, and our question asks to find the work done from the graph, starting from displacement equals to 0 until 8, from 8 until 10, and from 0 until 10. For the first question, it says from 0 until 8. So we can divide the graph, the triangle, which is from 8 to 0 to 8 by 2 to find the work done by using the formula for the area of triangle. In this case, it's 1.5 multiplied by 4, which is the difference in displacement, multiplied by 6, and it is equal to 12. This one is one part of this half triangle. If you want to find the another part, you can just multiply it by 2, because the triangle has the same values if you cut it by 2. That's why our work done, because of the shape of the triangle, will be 12 plus 12, which is just 24. The next is the question B, which asks us to find the work done from displacement 8 until 10. In this example, we can see that the force is negative, which means the force is going to the left because it's going to the negative direction. So we're going to use the negative value of this force, which is -3. And then we can see that from 8 until 10 is just one triangle. So we still use the area of triangle for this equation, which is 1.5 multiplied by the base, which is in our case is displacement, change in displacement, which is 2. 10 minus 8 is 2. And then multiplied by -3, which gives us just -3 joules. The C asks from 0 until 10, which we already initially calculated. Because work done by a force can be negative, because it just indicates the direction. We can, even for the work done from 0 until 10, we still need to use the negative value that we got. In this case, 24 plus -3, the negative value, and it's equal to 21. The next question is given like this. It shows a block being moved from one place to another with a displacement and a force. Our force is equal to 16. It gives us the mass, which is 2.5, and it gives us the theta, which is the difference in angle between force and displacement. And then it also gives us the change in displacement. So this question asks us work done by applied force, the normal force exerted by the table, the gravitational force, then net force on the block. So we already talked about that the normal force and the gravitational force is equal to 0 when the block or the mass doesn't change its displacement vertically. Because of that, for the questions B and C, we already know that the work done is equal to 0, while the work done by applied force is equal to 16, the force, 16 newtons multiplied by 2.2, which is change in displacement, multiplied by cosine 25, which is the angle between the force and change of displacement, which gives us 31.9 joules. And the work done by net force is actually just the grouping or just the sum of all of the work done in this system. In this system, the only work done is done by the force of application. That's what applied force. That's why the work done by net force is just 31.9. So that's all for today. Thank you for watching my video, and I hope your exams will be as easy as the examples that I gave you, and I hope you have a good night. Thank you.